All right, open your book up to section 10-4. This is quadric surfaces and inscribed figures. This is on page 516 in your book. We've already covered the first half of this objective. Given the equation of a conic section, sketch the surface generated by rotating it about one of its axes. That was what we did in the first half. Now let's tackle the second half, which is to find the area or volume of a figure inscribed either in the plane bounded by the graph or in the solid region bounded by the surface. All right, so let's take a look at an example there in your book. Look at example number 2 on page 516. It says rectangles of various proportions are inscribed in the region under the half ellipse 64x squared plus 25y squared equals 1600 for y greater than or equal to 0. Let's go ahead and write down that equation here first of all. 64x squared plus the 25y squared is equal to 1600, and that's for y greater than or equal to 0. It says that a vertex of the rectangle is the sample point xy that lies on the ellipse. The rectangle can be tall and skinny, or short and wide, or somewhere in between, depending on where the sample point is placed on the ellipse. And of course, the area of the rectangle will depend on the location of that sample point. And it says to place the sample point in quadrant 1. And they give you a sketch of what this should look like over there on the next page, but let's just verify that that in fact is the sketch we should have there. Let's take this equation and get it into its center radius form. So we can do that by dividing by 1600. So if I take 64x squared and divide by 1600, and add that to 25y squared divided by 1600, that's equal to just 1 when we divide everything by 1600. And in fact, this simplifies here. 64 over 1600, that's just x squared over 25. And 25 over 1600, that simplifies to just y squared over 64. And that's, of course, equal to 1. And we can get this into its center radius form here. If I just simply write these as perfect squares, I can write that as x over 5 quantity squared plus y over 8 quantity squared, and that's equal to 1. All right, so this is in fact an ellipse. It's centered at the origin. It's got an x dilation or an x radius of 5 and a y dilation or a y radius of 5. So we can sketch that then. We'll sketch that over here on the side. So that's -5, and we'll put +5 here. We'll say this is 8 up here. So we have this semi-ellipse. It's the top half of this because we're saying y is greater than or equal to 0. So there's our sketch of this semi-ellipse. And what we're going to do is we're going to inscribe inside this conic here, inside this ellipse, a rectangle. So I'm just going to pick some sample point here, and I'm going to draw a rectangle that uses that as one of its vertices, and I'm going to name that sample point, like they said, name it as xy. All right, so take a look at what part A says do. Part A says to write the area of a representative rectangle, that's what I've got sketched here, in terms of the values of x and y at the sample point. Okay, so for part A, got to go back and refresh my memory on how to find the area of a rectangle, but we should all remember that area of a rectangle is just base times height. That's how we calculate the area of a rectangle. So if we go over to our sketch here, the base of this thing is this distance right here between these two blue lines that I've marked here, the two sides of my rectangle. That's the base. So notice that that right there is actually related to x in terms of that xy point I've got labeled there. But x is only measuring this horizontal distance right here. It's the distance from the y-axis to that point. So it turns out then the base is actually equal to 2x. So I can replace in my formula here that area is equal to base is 2 times x. And now let's take a look at the y value. The height. The height of this is going to be this vertical distance here. That's our height. And that's exactly what y measures. Y measures how far that point is from the y-axis, or from the x-axis. So that's this vertical distance right here is actually what y is measuring in terms of that xy point. So that's the same as the height. So I can replace the height in here with y. And so my equation here for the area is equal to 2x times y. All right, step 1 done, or part A is done. Part B says transform the equation in part A so that the area is a function of x alone. So they want me to get this in terms of just x, get rid of the y, in other words. That's what part B is asking. Well, to do that, I need to know a relationship between x and y, where x and y is that point over there. Well, that point is not only a point on the vertex of my rectangle, it's also a point on the ellipse. And I know the relationship between x and y on that ellipse. In fact, they told me that in the problem. It's this equation here, 64x squared plus 25y squared equals 1600. So let's write that down. We have 64x squared plus 25y squared is equal to 1600. And we want to solve this for y. So let's subtract the 64x squared. I'll have 25y squared is equal to 1600 minus the 64x squared. Divide by your 25, so we have y squared is equal to 1600 over 25. That turns out to be 64. We've already done that arithmetic earlier. And then 64 over 25, I think I'll just leave it as that. 64 over 25 times the x squared. All right, solve for y. Take the square root of both sides. So we have y is equal to, actually you get a plus or a minus here when you take the square root. But remember that the original problem said that it's only a half ellipse, first of all, and it said that y was greater than or equal to 0. In fact, I probably should have written that up here with the original equation again, that this was for y is greater than or equal to 0. And that's how I know that I'm going to pick the positive part of this here. It's the plus or minus, but I'm going to pick the positive one. Again, that's because of the fact that y has to be greater than or equal to 0. Okay, so with that, we can replace y in our equation for the area. Earlier we said in part A that area is equal to 2 times x times y, and y we just found out is equal to this square root. The square root of 64 minus 64 over 25 x squared. All right, so there's our equation for what the area is equal to as a function of x alone. All right, for part C, it says make a table of values of area as a function of x for each 1 unit from x equals 0 to x equals 5, and based on your table, approximately what value of x is in this interval seems to give the maximum area. Okay, so go ahead and grab your calculator here and let's try this out. Okay, so in y1 we're going to put our equation. Again, our equation was 2 times x times the square root of 64 minus 64 over 25 x squared. All right, just make sure that you got that punched in there correctly there. It's not a nice equation there, but nonetheless, this will be our equation that will give us the area. All right, they said make a table of values, so we'll go ahead and make a table of values. If you go to your table setup, we'll start our table out at 0. They said to go with increments of 1, and we can go to second table, and there we go. Okay, and we get the values of 0, and then 15.6, 29.3, 38.4, 38.4. Probably somewhere in there is where we hit our highest point. That's what it was asking us for. And then it's back to 0 again at 5. In fact, let me just grab a picture of that and we'll put that in our slide. All right. And now let's take a look at part D there. D says now plot the graph of the area as a function of x and use the maximum feature on your grapher to find the value of x that produced the maximum area to find that maximum. Okay, so we're going to go to our calculator. Now that I can see the set of data there, that table was nice to be able to see. I can actually come up with a decent window to sketch this in. So let's go back to our calculator and go to our window. Again, we're only interested in what's happening from 0 to 5. And our scale is 1. And it looked like we went all the way up to, 38.4 or almost 40 there, it looks like. So I'm going to actually do that, go up to 40. It might actually go above 38.4, most likely it does. And probably a scale of 2 will be fine there. And we'll graph that. Actually, 40 just barely fits on the screen there, but that does, in fact, fit on the screen there. We're looking for the maximum, so you can go to your second calc menu, and you can go to maximum. And we'll give it a left bound, sure, 2.5 is fine. I'll give it a right bound of, say, 5. And I can give it a guess of somewhere between there, let's say somewhere around 4. We'll give it as a guess. So it turns out, there we go, the maximum is 3.536 if we round that. And the y value there is 40. Again, let me grab a picture of that. We'll put that in our slide. All right, and that was part B on this one. And the question they asked us here was to determine, plot the graph as a function. Use the maximum feature on your grapher to find the value of x that produced the maximum area. So we're trying to maximize area. So our maximum area turns out to be at this x value of 3.536, I guess. X equals 3.536. And the y value here is actually representing for us the area. So the maximum area then is 40. I'm going to just call it area, or A is equal to 40. All right, and there's how we set up that problem and solve it. One other thing we should do here, by the way, when we go to sketch this thing, when we actually come up with our equation here for the area, we should indicate the domain here. They kind of helped us out in part C there when they said create this table, but we should go ahead and indicate that as well, that the values of x that make sense in this problem is that x has to go between 0 and 5, and if you go back to your sketch to see why, you can see that that sample point, you can move it all the way to the left. They said stay in quadrant 1, so all the way to the left there is the y-axis, and then all the way to the right would be where we hit the x-axis, and that would be at 5. So that's a reasonable domain for this problem. All right, we also want to be able to find the volume and surface area for some solids. So let's go back and refresh our memory here a little bit with how we find the volume and surface area of some different shapes. Let's start with the cylinder. The volume of a cylinder is pi r squared times the height. The lateral area is the area excluding the top and the bottom of that cylinder. The top and bottom of that cylinder is circular, so we're excluding those. So the lateral area is just the 2 pi r times h. And the surface area includes the top and bottom as well as the lateral area. So the surface area is 2 pi r times h plus 2 pi r squared. They have these formulas at the end of this section there, so if you need to flip there to remind yourself of those formulas, or as you're solving some of these problems, just find them at the end of this section here. A cone, if you're looking for the volume of a cone, the volume of a cone is actually 1/3 the volume of that cylinder we just described. It's 1/3 pi r squared times height. To find the lateral area of a cone, it's L is equal to your pi times the radius times L, where L is the slant height of that cone. And that excludes the base, circular base. The surface area includes that. Surface area is the lateral area plus the bottom of that. So that's pi times the radius times your slant height, and then plus the pi r squared for the area of the base. And finally, the sphere. If you're trying to find the volume of a sphere, the volume of a sphere is equal to 4/3 pi r cubed, and the surface area is equal to 4 pi r squared. Those are some formulas that you've seen in the past, but probably a little refresher here will help us out in solving some of these problems. All right, so let's take a look at one more example here. Look at example 3. on page 518. Example 3 now says the part of a parabola, y equals 4 minus x squared, in the first quadrant is rotated about the y-axis to form a paraboloid. A cylinder is inscribed in the region under this surface with the center of its lower base at the origin and the points on the circumference of its upper base on the paraboloid. All right, so let's write down that equation that they gave us here. Y is equal to 4 minus x squared. And it's in the first quadrant, so we're in quadrant 1. And it says that we're rotating about the y-axis. So I like to draw a little circular arrow here to indicate we're rotating around the y-axis. All right, we're going to form our paraboloid. So let's first sketch what that looks like. Y equals 4 minus x squared in quadrant 1. So 4 minus x squared, that means we're going to cross the y-axis there at 4, and we're going to cross the x-axis at 2. So it's going to kind of look something about like this. There is our parabola. And we're going to rotate that around the y-axis here. So we're rotating around this axis down here. And so we'll end up with something like this. I'm going to sketch the other side of this parabola here to help me sketch the paraboloid. And we sketched some of these the other day. So we should end up with something that kind of looks like this. There's our paraboloid. Now it also says then you're going to take and inscribe a cylinder in that region under that surface. So let me draw what the cylinder looks like. So let's pick some point here. We'll pick this sample point right here, and I'll draw ourselves a cylinder here that would look something about like this. And we'll call this our sample point XY. So we've got a cylinder inscribed inside of our paraboloid. All right, and it says for part A, sketch the paraboloid and the cylinder. That's what I've got there. That's part A here. Got ourselves a sketch of it. We'll label that part A. Part B now says to find the volume of the cylinder as a function of its radius. Volume of a cylinder. Well, this is one of the formulas that we just looked at there. To find the volume of a cylinder, volume is equal to pi times your radius squared times your height. That's the thing you got to know to start off with. Just like the last example, we had to know the formula for the area of a rectangle before we get started. And now let's see how the radius and height relate to our sketch here. So I'll mark those here. If we were to measure the radius is this distance right here. That's our radius r. Well, notice that's the same distance that x measures in that sample point xy. The height of that cylinder is this distance. That's the height. Notice that's the same distance that y measures. So it turns out I can replace the radius and height and put this in terms of x and y. So it's pi times the radius is x, so it's x squared, and the height is y. So I can replace the height with y. So there's our equation, pi times x squared times y. They want me to write this as a function of its radius. So the radius again is x, so that means I want to get rid of y. I need to know what y is equal to. Well, in the last problem, we had to solve for y to substitute in. In this problem, that was nice of them to actually tell me what y equals. Y is equal to 4 minus x squared. Notice that point xy is a point not only on my cylinder that's inscribed inside of this paraboloid, but it's also on the parabola. So I can just simply substitute in for y. Y is equal to 4 minus x squared. So it's pi times x squared times 4 minus x squared. There's our equation. And let's go ahead and indicate the domain for x in this problem. So for x is staying in the first quadrant, and I can slide it all the way to the left when I hit the y-axis. That's as far as I want to go. That would be x equals 0. And if I slide it all the way to the right when I hit the x-axis, that's where x is equal to 2. So it looks like our domain here that makes sense is that x is between 0 and 2. So go ahead and indicate a domain that goes along with that function you've defined here for the volume. All right, part C now says find the maximum volume of the cylinder can have and then find the radius of this maximum cylinder. Okay, so for part C, we're going to grab our calculator to help us solve this. We want to maximize the volume. That's what we're trying to do. So let's grab our calculator and let's punch that into our calculator. All right, so here we go. Let's punch in our equation here. Again, it's pi times x squared times the quantity 4 minus x squared is the equation for the volume of the cylinder. And we've already figured out that the domain for this that makes sense is from 0 to 2. And again, let's use our table to help us come up with a decent window to sketch this in. So if we go to our table setup, we can start it out at 0, but this time let's change by, say, 0.2. I just want to see enough points here that I can get a good idea of how big of a window I need to set here. It looks like it starts out at 0. It's increasing all the way up to 9, 11, 12, and then goes back down to 11, and 7, and 0. So it looks like if we go up to, say, 15, we should have a decent window of this. So let's go from 0 to 15. And we'll graph that. There we go. There's our sketch of the equation that represents the volume of this cylinder. And we want to just find the maximum. So let's go to our second calc, go to maximum, and give it a left bound here. 1, sure, that's fine. We'll give it a right bound. I'll say 2. And I'll give it a guess here of about 1.5, somewhere in the middle there. And there we go. 1.414 is our value of x. And our value of y, which is representing volume here, is 12.566. So let's grab a picture of that, and we will paste it into our slide here. And let's go ahead and write down what values we got here. So for the maximum volume, it turned out that x was equal to 1.414. That might be a number you recognize. If you don't, that's fine, but that looks like the square root of 2 is what that looks like. And our y value, and our y value here is representing volume, so I'm just going to say V is equal to 12.566. All right, and the last piece of this, they said find the maximum volume of the cylinder can have, and then find the radius of this maximum volume. So that's just kind of remembering what the x and the y represent here. Again, the y value in this equation was the volume. The x value for us was actually the radius. This is where your sketch will help out if you need to. Go back up and see how you measured the radius there, but the radius was the x value. So this actually is the radius, so I don't need to find anything else. We've already found what we needed to.